The next type of problem we're going to solve using the double angle identities is an identity verification. So we're going to verify that this identity is true. Again, this is just like any other two-column proof idea where we're going to work either with one side or the other, writing down our rationale for each step that we make, and then hopefully we can get them to be equal at the end. Okay, we're going to assume they're not equal, even though I have the equation written up here. And we'll try to work from one side or the other or both and try to get to a common expression. When I look at this one, I could start on the left side. Cosine of 2x, well, I have an expression for that as 1 minus sine squared, or I'm sorry, 1 minus 2 sine squared, or 2 cos squared minus 1, or cos squared minus sine squared. Either of those three options. Because I don't know, I could choose any of them and try to move forward, and if I get stuck, I could switch over to a different formula and move forward. But because there's a bunch of options there, I may actually just try starting on the more complicated side. This one looks more complicated to me. And maybe try to work from there and eventually get to the other side, to the left side. Just an option, just something as I'm looking at it. I try to look at what I think is more complicated and try to simplify it rather than I think this one looks simpler and it has more options. So I think I may end up going down a wrong path, by just choosing the wrong option and having to do more work that way. So I'm going to start on the right side and work that through. So I'm going to ignore what's on the left for a moment, even though I'm aiming for this as my goal. And we're going to take the right side and we're going to say that as I'm looking at this, there's some options here. The first thing I see is that 1 plus the tangent squared reminds me of a Pythagorean identity. I know that 1 plus the tangent squared is equal to the secant squared, because that's one of our Pythagorean identities. So let's go ahead and make that replacement first. We'll say that this is 1 minus the tangent squared x all over the secant squared x. Oops, did I write that, spell that right? There we are, secant squared x by a Pythagorean identity. Okay. Now when I have one term in a denominator, I usually like to split that up to the numerator and try to simplify each fraction separately. That might move us forward from there. So let's go ahead and do that. Let's split that up and call that 1 over the secant squared minus the tangent squared over the secant squared. All right, so I've just split that up. This is a distributive property, essentially. Right, it's distributing that denominator, that division, to both terms on top. Now I look at this and I say, well, 1 over the secant squared. Well, what's the reciprocal of the secant? It's the cosine, right? So 1 over secant squared is the same as the cosine squared. So this would be cosine squared of x. I also know, let's do that again here. Let's actually change each of these, the tangent and the secant, into sines and cosines. Maybe that would move us forward. So the tangent is the sine over the cosine. I don't want to write this. Sine over the cosine. Because I'm squaring it, I would square each of those. So it's sine squared over cosine squared. All right, that's the tangent. We're then dividing by the secant squared, or multiplying by 1 over the secant squared. Okay. Now the 1 over the secant squared is the same as the cosine squared. I should probably write a reasoning for this. This was using a reciprocal identity and a quotient identity. So it's two things in one. Reciprocal and quotient identities. I'm going to utilize another reciprocal identity here and call this 1 over secant squared the cosine squared. So this becomes cosine squared x minus the sine squared x over the cosine squared x times the cosine squared x. That's a reciprocal identity. And then finally, I'm going to be able to cancel off a common cosine squared from the top and the bottom. And I'll be left with just a sine squared x on the second term. Okay, so this will become the cosine squared x minus the sine squared of x. And that's just canceling common factors. And I'm just about to run out of room, but I think I could squeak the last step in on the end. Now that I have cosine squared minus sine squared, I notice that that fits my formula for the cosine of 2a, or 2x, I guess, in our case. All right, so cosine squared minus sine squared is the same as the cosine of 2x. And that's using our double angle identity. Double angle identity. Sorry, my handwriting got a little bit sloppy down toward the bottom there, but that will be good enough. So this last line then matches the original other side of the equation that we were trying to work toward. And so we do end up verifying the identity that we sought to verify. Again, remember, had I started on the cosine of 2x, if I had started with that side, I would have had to make a choice between these three formulas. And it turns out the top one is the one I would have needed. Had I chosen one of the other two, I may have gotten, some work done and gotten to a dead end and not really been able to link it to the other side. And so you end up doing a little bit more work because you gotta wipe that clean, try another formula, which is fine, nothing wrong with that, eventually you get there. But I think it's easier to work with the side that doesn't have as many options, but is more complicated, and then you can kind of simplify down from there.